Hey, can you hear me okay, Scott, out there? Yay! Good morning, everyone. How are we doing? Thank you. Are there any questions to begin with? Michael?
Yeah, so what are you exactly expecting for the thing that's due on Wednesday? Is it like just like a Word doc or like a presentation or something?
No, a document's fine. Word, PDF, something along that. If you have activated the accessibility features of the computer you're sitting in front of, it now assumes that you cannot see, so it's going to speak to you instructions. Yes, well done. Katie, did you have a hand up? Yes, it is due Wednesday at midnight. So the D2L turn-in bin isn't open yet. I need to enter in all the teams so that it knows who belongs to who. And I do that this afternoon after my 2 o'clock research meeting. So sometime this afternoon, that D2L box should be open. I don't know. What did I just say? Dropbox. Dropbox will be open soon on D2L. A document, yes. This is a written report that I expect to have complete English sentences and pictures to explain stuff. Okay? All good? We all know how to use a spell checker? Yeah, you all say that, and yet, yeah, anyway. Any other questions about the assignment due on Wednesday at midnight? Joseph? Yes, I will still be there tonight at 9 o'clock, giving short little practice Java programming exam type questions for those of you who find that to be valuable. And I'll be there to answer any questions about the assignment after that as well. So yeah, please feel free to stop by the lab tonight at 9. The 310 lab, not the 101 lab, the 310 lab. That's my research lab. Other questions? All right, so where do we leave off? I believe we've gone through all the bits of our binary search tree except for 2 kind of important must-have methods, right? We have not yet actually added or removed anything from our binary search tree. We've just basically iterated through it and searched it and all that kind of stuff. But you can't actually get anything in there without the add method. So let's talk about add. Yes, present. Okay, do that. Here's your QR code just briefly if anybody wants to grab it before we start doing code. That one. All right. Search tree. All right, so we finished or stubbed out most of the rest of these ones that are useful. Add is the second to last one of real complexity that we need to talk about to finish off this chapter, and then we'll finish off with remove in the end. So there's a bunch of ways that you can add nodes to a binary search tree, but I'm particularly interested in the recursive solution because I think that's the most elegant and the easiest to understand in terms of how to add to a recursive structure like this. So once again, we have this funny case where the interface for our collection class requires that add be a method that takes the element we want to add and returns true if it succeeded in added it to the binary tree. But for the purposes of our recursion, we actually need a function that takes an additional parameter and that returns something different. And so we're going to follow the same kind of pattern we did up here earlier when we did a contains that was basically a stub to call a recursive contains, right? And a size that was a recursive stub to call recursive size, right? Same kind of story down here. There's going to be the actual add that's part of the interface, and then there's going to be the real recursive add that does the work for us. So I'll write this one first because it's pretty straightforward. I'm going to say root is equal to recursive add of the element that we want and the existing root, and then return true. All right, so a couple pieces here. First of all, how do I know that I'm going to return true? The whole purpose of this collection class interface for add is that I can get a signal back from the add. I can get a false if for whatever reason I'm not able to add this to the data structure. So why is it just return true for adding to my binary search tree? What is the case that would cause this to be false in some other collection class data structure that doesn't apply here? Joseph?
It would be full?
Yeah, it would be full. But this is a dynamic data structure where we allocate more nodes and more levels of the tree as we need it. And so unless the Java virtual machine actually runs out of memory and allocating a new node fails, in which case we're going to get a memory out of bound, or what is that exception? I forget. Memory exceeded exception that basically crashes the virtual machine. So there's really no point in watching for that case, right? We've got gigabytes of RAM to work with. We're probably not going to run out of space. It's not like all the collection classes that we've built that were built around a static array where we could run out of space. So we're going to succeed. We're going to be able to add a new node. And so the return true. But this part's the really confusing bit, right? So it's not weird that I have a recursive function that instead of just getting the element also gets the root of the tree, right? I'm in this class that implements the binary search tree. One of the fields that it has available to me is the root node of the tree. And that is not available to the client code that's using this binary search tree to store and retrieve data. And so we pick up that extra field and we pass that in as a second parameter. But the part that may look really weird is I'm resetting the value of root to be equal to whatever this recursive add function returns. So why is that? Why do I need to structure this so that whenever I call my recursive add function, what it's returning is not the true or false that I was expecting from the outset from this Boolean function. What it returns is the node that is the root of the new tree. Why does that have to be the case? Even before we've started to write this recursive add function, why must it be true that this recursive add function returns to me the binary search tree itself after it's made the addition? Because I can try to implement this in some other way, but looking ahead, I can tell you we're always going to end up back in this situation where we need to be able to return the tree itself and assign it to the root. Liam?
Because when it's adding a new node, it's like walking down one of the sub.
It is true that when we're adding a new node, it is walking down the subtree, but there's an even more basic case than that that necessitates me having the code structured this way. What is the simplest case for adding a node to a tree that we can think of? What is the recursive base case, in a sense? Alex?
There's nothing in the tree.
There's no tree yet, right? The value of the field root is null because I've just created this binary search tree and I've never inserted anything into it yet, right? That's the most basic case. It's going to come up right away. And if I'm making a recursive add function, the result of me calling that function has to be that the root node becomes not null. It becomes the first node that I'm inserting into the binary search tree, right? So we can make a function that doesn't return that root, but then that function is going to have to be able to change the value of root that is stored in this binary search tree object. And basically, it's going to be what we call a hidden side effect, right? So I could write the code so that it doesn't do this, but that would then hide the fact that every time I call recursive add, potentially it is changing the very node that I am pointing to in the tree. And the first easiest case to see that is, what if the tree is empty to begin with? Well, then calling recursive add, it's going to give me back the root of a brand new tree, right? But this is also true for when I'm adding down each one of the left or right subtrees. at each individual node, when I'm trying to recursively add that node to one of the subtrees, the end result is calling this recursive add function is going to return to me a new subtree that has the node added that I've asked for. It might not be changing the node right at the top of that subtree. It might be adding it somewhere down the way. But somewhere along that chain, there was a place where this assignment is going to change the value of the node that I was looking at. Does that make sense? So because of the nature of the recursive add, we end up with this structure for calling it. All right? And once we commit to that, it actually becomes a lot easier to figure out what the cases are for actually implementing this recursive add function. So that's the stub. That's super, super easy once you get your head around why we're going to do it that way. But we actually still have to write the add function that's going to do all the work, right? This recursive add. So that's going to be a private function because nobody outside of our code should be able to call that. It's going to return a binary search tree node, parameter type t, because that's what's got to be here if this line up here is going to work correctly, right? Recursive add function. And what it takes as parameters are an element of type t and a binary search tree node, generic type t, that is basically the node that we're on for the purposes of addition. All right, so this function is going to do all the real work of adding to my binary search tree. Okay, so what are the cases that can come up here? We already talked about what the first, most basic one is. What if node is null? So either the tree itself is empty, and this is the very first node that I'm adding to, or potentially I've already recursed down a bunch of levels in the tree, and I've made my way to the leaf that's next to where this item should be added, and I've called my recursive add function on its left or right null subtree, because it's a leaf, it has no children, right? Both of those cases are going to be wrapped up into checking whether or not node is null. So not only because this is the rule for all of my recursive functions, that I always have the base case first, but also because it just structurally makes sense that this is going to be the thing that will happen when I find the place where I should add something. We check whether node is null. If node is null, then that means I am in the place where this thing should be added, right? If I'm at the root of the tree, this is the very first node and I'm making it. If I've made my array recursively all the way down to some leaf down at the bottom, I've found the leaf that I should be adding this node to as a new child to that leaf. And so it's the same case in either one of those. So I'm going to allocate my new binary search tree node, type t. I'm going to pass in the element into the constructor because that's the thing I've been trying to add all along. And that's actually it. I'm done. I'm done with that base case. The interesting case is, of course, if it's not, right? So if the node is not null, then that means there's at least one item in this subtree that I'm looking at. And now I have to decide, does the new element that I'm trying to add, does it go to the left or does it go to the right? Yeah? And because of the additional abstraction that they've built into the textbook version of this, we've got this comparator thing sitting around that allows us to sort of change the way that we compare the underlying nodes using this compare method that's built into it. So that I realized that was like a full week ago that we wrote that code, but when we built the top part of this class, we talked about there being a comparator object that we could pass in that would change these decisions. So there we are. We just throw that in, comp.compare the element to the info that's stored at this node that we're on, right? That comparison method is going to return an integer, and if it's less than or equal to 0, then that means this item that I'm on goes to the left subtree, right? So if that's the case, I feel like I should put a space there for propriety's sake. Then we're going to say node.setLeft to be the result of calling my recursive add function. I'm going to add the element to the current left subtree. Oh, boy, that's a lot, right? So this is basically the interior node version of this assignment up here. The base of this line is I'm calling the recursive add function. I'm giving it the element that I'm still trying to add and the left subtree. The result of this that comes back is the new left subtree. And I want that new left subtree to replace whatever the current left subtree is on the node that I'm on. Right? And so the way we do that once we're actually into a non-null node is with this set left method. But, you know, if we had made the left and right fields of our binary search tree node public members and weren't using getters and setters, this would totally just be an assignment statement here, right? All this set left code is doing is saying, yeah, take this value that's passed in and set the field name left to be that value. So it's very much the same as this assignment statement up here, except it's just the left subtree. You with me? I know sometimes the recursion hurts, but I think this makes sense if you follow along with what it's doing. All right, so one more case. If it's not going to the left, then it has to go to the right. So notice the way we're adding to this binary search tree, we never replace the node that we're on. Right? We're always adding to the left or to the right. And so we're always adding children to the existing tree, whatever that is. So if it doesn't go to the left, it goes to the right, which looks awfully similar. We just replace all the words left with word right. Same pattern. Right? And after all of that, remember, this recursive add method returns whatever new tree we've built, and that is this value of node, right? It's either the brand new node we made in the base case, or it's the existing node that we were given with either its left or right subchild replaced recursively with the new subtree that has the thing added in the right place. So can you picture how this works? Do I need to draw some tree diagrams, or can you model this in your head, how this is going to work if I start adding things to the tree? Yeah? Okay, I'm seeing mostly positive nods, so I'm not going to bother to draw that out. Let's move on to remove, because that's a little bit more challenging. There's more stuff to think about in the case of remove. So once again, we need to actually make this recursive. You can do an iterative remove, but I think it's a total waste of time to worry about the code for that. So I'm going to more or less ignore that and do the recursive case instead. It's going to have the same overall form as my recursive add. So I'm replacing the root node each time, because potentially in the most basic case, there's only one node in the tree. I'm asking to remove it, and the result will be that root becomes null, right? I'm going to take away the one node that's there. And so this recursive remove function needs to be able to change the value of the tree that I'm currently looking at. So we say root is equal to the result of this recursive remove function. You can't really return two values in Java. And so even though that recursive remove function is really going to be doing two bits of work for me, it's going to be giving me back the new subtree with the item I want removed, but it's also going to be returning a Boolean value found that indicates whether I found the item along the way. Well, we'd like to be able to return both those values from this recursive function, but Java is a language that doesn't let me do that. So we're going to do the thing that I said we shouldn't do about 10 minutes ago, which is have another external field variable found that is kind of like another return value from this function. So my recursive remove function is going to set the value for found to be true or false. And then out here, I can pick that up and return that as the overall result of the function. But inside the recursion, the only thing that's being actually returned by the function is the new subtree. Does that make sense? There are some programming languages more crazier than Java, Or we could actually set that up where the recursive remove function always returned two things to us, the new subtree and a true or false that indicated whether we found the thing. But that's not the way Java or C or C++ or C# does things. So we'll use this extra found field, which, if you recall, way up at the beginning last week, we already defined this found variable as a field here, right? We haven't used it yet, but it was there already waiting for us. So what do we need to do to remove a node? We've got three cases. So let me draw a little tree here. I feel like I've drawn this diagram like 5 times already, right? So case number one. Case number one is I want to remove, oh boy, that's terrible. Try that again. That whole thing was terrible. Case number one, I want to remove a leaf node. All right, so if I want to remove this one, it's pretty straightforward. I'm just going to recurse down from the root until I find the one that needs to go away. Because it's a leaf and it has no children, I'll just be able to take that out. All I need to do is replace the left side pointer of the parent node with a null, and it will be effectively removed, right? So that's easy. I probably should have duplicated that diagram 3 times so that I could do this a little bit faster, but I didn't think of that. Case number two. Case number two, I need another node here. Or one less node, that would work too. There we go. Case number two, I want to remove a node that has one child. So if I'm trying to remove, if I'm trying to remove this one here, it's pretty straightforward what I do. I take the child, oh, crazy. I take the child node and I promote it to the parent's spot. Right? Because there's no right subtree, I can just promote that child, and the node that I wanted to be rid of is out of the way, and I've got no problems. And this works even if that child node itself was the parent of a whole bunch of other tree, right? That's okay. That's not going to bother me because it'll still work correctly, right? Okay, case number three. There ought to be a faster way to do this. Maybe there isn't. I just haven't learned it yet after all this time. Case number three is the interesting one. What if I'm trying to remove a node that has more than one child? Let's say I'm trying to remove this one here. Red. If I'm trying to remove this one here, well, I can't just get rid of that node and replace it with one of the children, because potentially that screws up the ordering of the binary search tree, right? If I've got a bunch of trees down here, then if I just take one of the children here and promote it up, I might be breaking the ordering of the binary search tree. So who is eligible to become the new parent node here if I'm getting rid of the one circled in red? That will preserve the correctness of the binary search tree. Nicholas.
Would you keep parent node then to just assign, or you would just,
Which root?
or like the original root, or you remove that or replace it with the parent node of one circled in red?
Replace it with this parent node?
Yeah, or
That might also break my binary search tree.
yeah.
Okay, so let's remember our ordering. What's the rule here? So I've got a node here, and it's got children down here. I should probably draw a few more children to thresh out this argument a little bit better. What's the ordering between these in this subtree here? Which of these 1, 2, 3, 4, 5, 6, 7, which of these 7 nodes in this subtree has the lowest value? Which one is 1? Yeah, but I wasn't paying attention. Bottom row farthest to the left. This one here, right? This one has the lowest value. This one has the highest value. This one is right in the middle, right? So who has the values adjacent to this node here that I'm about to kick out? Yeah, the 2 that are in the middle and the bottom here. Or to be more specific, the rightmost child in the left subtree, or the leftmost child of the right subtree, right? So it's going to be one of these 2. No, do not do that. It's going to be one of these 2 down here that is adjacent. Well, these 2 are the ones that are adjacent to the node in red, right? So if my goal is to find a new candidate to be this node here, the parent of these 2 children, I want one of these leaf nodes all the way down at the bottom, or I want one of the values in one of these leaf nodes all the way down at the bottom. And it actually doesn't matter which one, in a sense, right? By convention, because we've been talking about trees where any value that's less than or equal goes to the left, we tend to default to the rightmost subchild of the left subtree, this one here. But its buddy over here is also perfectly correct. But when we write our code, we're going to pick one or the other, right? We're not going to write the code to go find one of the 2. We're going to code it up so that it always does this one, for example. All right, and that's exactly what the book's going to do. Now, moving nodes around in the tree is kind of a hassle because we've got a whole bunch of links that already point to this particular node, right? There's a parent link that points down to this one. This one has links left and right to these subchildren. I don't actually need to get rid of this node in the tree. I simply want to supplant the value in its info field. I want to get rid of its payload, right? It's actually a lot easier for me to nuke one of these leaf nodes down here, steal its payload, and replace it here in this part of the node, right? That's going to be easier to do. So that's what we're going to do, is we're going to take the payload from this node, replace the payload in the red node, and then the value that was in there, we're just going to get rid of that, right? Throw that out because that's the thing that we're removing, right? And then eliminate this child down here. Are there enough colors and X's and circles in that diagram for you to follow anything that I said? All right, so that's the strategy. So single leaf with no children, that's easy. Just nuke it out, right? Node with only one child, that's easy. Promote the child and all of its subtree to take the place of this node. Complex case, I've got 2 children, left and right, and I want to find one of the adjacent values and replace the payload in place in the parent node with that value and get rid of the leaf node where it sits. And the one we're going to pick is going to be the rightmost child of the left subtree. Do we know there is a rightmost child of the left subtree? Do we know there is a rightmost child of the left subtree? Jake, you're shaking your head no. Why not? Why do you think there might not be?
Well, I mean, That's not like there isn't necessarily always going to be that node. It's possible that oh no, if there's 2 children, then that node has to be filled because then it would go over to the right side.
Right. So by merit of the fact that we're in this third case, we know that there's got to be a subtree on both sides. So there certainly is a subtree on the left here. Is there going to be a rightmost child on the left? By definition, there has to be a rightmost child. But it might not be so simple as, oh, and it's a leaf dangling all by itself over here on the end, right? It could be more complicated than that. What's the most irritating complication we could have? So it could be there's only one child on the left here, in which case the rightmost child is the only child, and so that one gets promoted up. That's pretty straightforward. It's pretty straightforward if that subtree then has, leaves off to the right here. What's the most irritating case that you can envision that's going to come up here?
If the left child doesn't have a child to the right, and the right child doesn't have a child to the left, and so they both just keep going the other way.
Oh, yeah, that's going to suck, right? Let's draw that out real quick so you can visualize what it's going to look like. So the worst possible case that can come out of this, that's going to be just the most irritating one, is I'm trying to get rid of this node here, right? Now do that. But that node only has a subtree that doesn't have a rightmost child, right? So which node am I identifying to steal the contents of? This is the rightmost child of that subtree, right? And it's not a leaf dangling. It's a parent with only one child. So what do I do in that case? Here's where we do a meta level of recursion that will cause like about a third of your heads to explode. Alex? Just a third. We'll see. I don't know. You ready?
I was gonna say, couldn't you just write a method? You can choose either the right or the left, and recursively have a temporary node, and then search through and check if the next right node exists. You set that node equal to the right node, and otherwise you were just return it. So then once you reach a point where there's no more right nodes, it automatically just returns that as the one that you want.
I'm not sure I followed that.
So
I'll try again.
So you start if you're gonna branch, you want to pick the left side. And that's
All
where
right,
you're gonna
I'm picking the left
pick.
side. I'm going for the left side.
So then you write a method where you have you set some node variable equal to that first node on the left.
This blue one.
And then you search. You say, okay, you look to that node's right node, the one that would be to the right of that one.
But there's nothing to the right of this one.
Well, I mean, you could just as a generic algorithm that would do it. So then if there is none,
okay,
if it's null, then it just returns the value that's at. Otherwise, it sets that temp value equal to the right one, and it keeps recursively searching, trying to go as far right as it can. But in the case of that one, since there is no right one, it would stop right away and just return the first one.
Okay, but now how do I get rid of this node? Once I've identified this is the one that has to go.
Do the same method that you did where you would pop back, you could just, how you had a case where there's only one child, you just do the same thing and you.
Oh, yeah. What I really need is a way to remove this node from this tree, right? If only I had a function that if I called it, it would remove a node from a tree. Do I have such a function? Yes, I'm in the middle of writing it, right? We can recursively, while we're in the process of removing the red node, call the recursive removal function on the left subtree to remove this node from that subtree. Did you follow that sentence? Did your head explode? Only about a third of you. Okay, that's all right. So yeah, this is for sure the most irritating subcase, and we need to be wary of that. We need to be ready for that when we get to that point in the code. All right. but that's what's going on as we try to write this. All right? So let's get to it. So I've got my recursive remove helper function here. We need to actually write this recursive remove function. And this will be the most complicated conceptually of all the methods we've looked at so far. But it's well worth looking at because it's a super cool thing that exists in any actual binary tree recursive implementation. And once you've got this, it's all downhill. So recursive remove, I've got a target node, a target value that I'm trying to get rid of, and I've got the root of the subtree that I'm currently working on. We'll call that node. All right, what's my base case? What's the easy one?
The node you're passing in is null.
If the node I'm passing in is null, right? When I'm doing recursive methods over linked recursive structure like this, my base case is almost always is the node null, which is not only correct as the base case for the recursion, but also is a great defensive programming strategy because I don't want to call any methods on this variable called node if it's null. That will cause a null pointer exception and my program will crash. And so I always want to be checking is node null before I try to do anything with the node value anyway. So there's two fantastic reasons why the first thing I need to do is check whether the node is null. So this is my base case question. Is node equal to null? What if it is? What then should I be doing? What does that mean for my overall recursive removal if I've made my way down to some leaf and it's checking its left subtree and I pass in the null value of that left subtree into this recursive function to get to this base case? What does that mean for my search? No one knows. I've lost you all. Okay, simpler case. What if this is the very first time I'm calling this recursive removal function and the value of node is already null? What does that mean? Katie? Why? Yeah, there's nothing to remove. I've made my way to the appropriate point in this tree where there ought to be the thing that I'm looking for, or there was nothing in the tree to begin with, is the even simpler case, because the node is null. If the root is null, this will be what happens the very first time I call this function, right? And that means the thing I was looking for wasn't there. The user has asked me to remove a thing that's not in the tree. If I make my way down to here, to where a node is null, then either the tree was empty to begin with, or I've recursed down to the leaf where it ought to be, and it's not there, right? So found is equal to false. I mean, later on down the way, we need to also return whatever that node value was, all right? Because this says it's going to return the new value for the subtree after I've removed stuff. So if node is null, then I'm going to return null from this function, but I also need to set found equal to false. All right? So those three lines of code together make up my base case, but I'm going to separate them because return node happens to be what I'm going to do for all of the cases. Right? All right, so what do I need to check next? Well, just like my recursive add function, the next thing to do is to figure out, do I need to head left or do I need to head right? Yeah? Is that the next thing I should do? No, it is not the next thing to do. You guys are all just falling asleep watching me type in code. What should I check next before I decide whether to go left or go right? Remove is not the same as add. It's a different thing. What am I doing right now? What is my code supposed to be doing right now? I'm trying to find the thing that the user has asked me to remove, right? Where's the first place I need to check if this node is not null? Yeah, I need to look in the node that I'm on before I decide to go left or go right. It might be this one. It might be the node where I'm at. So this is more complicated than add, where we knew for sure we were adding a brand new node. The question was just where. In remove, we're trying to identify a node, which might be a leaf node, or it might be a root node, or it might be an interior node, where the item I'm looking for is already in the binary search tree. So we've got the base case, but then 3 different things we need to check for in the general case. Or you could think of this as, I mean, really, this is a second base case. The second base case is the tree's not null, but the item I'm looking for is here. It's in the node that I've made my way to, right? So else if, call that comp.compare function again. Can't type. So node.getInfo gets me the info stored in the node that I am on right now. I'm going to compare it to the target. If that is equal to 0, then I've found the one that I'm looking for, right? If it's less than 0, then I need to search left. And if it's greater than 0, then I need to search right. So we've got 3 cases here, right? Does it matter which order I tackle them in? In this case, it doesn't really matter which order I tackle them in. So it's OK either way. So I'm going to say equal to 0. Put in a comment here. It's here. I found it. Right? If it's here, then I need to remove this value from this subtree that I'm sitting at. Right? That's kind of complicated, right? We saw the 3 cases for what to do. So we're going to use another helper function. We're going to pass the buck to another helper function called remove node. It's this one. Right? We'll say we found it. All right, and we'll come back to what remove node does in a second. Otherwise, we need to check if we're going to go left or right. Ooh, too many ifs. If it's less than 0, then I know I need to go to the left, right? So we'll do node.setLeft. Because we're going to change whatever that left pointer is, and we're going to set it left to whatever the result is of calling my recursive remove function with the current target and the current left. Right? Or correct, I should say, since we're working on the left case. Do I set the value of found here? No, because I don't know whether found is going to be true or false in that left subchild. That's going to be the job of that recursive function to figure that out. So I don't need to worry about that. Else, come on, behave. Okay, it's annoyed at me. I must have not got my parentheses closed there. Here we go. Haha, that makes more sense. All right, else it's got to be to the right. Yeah, so same thing. Not at the node I'm on. It's not less than, so it's not to the left. So I got to set the right here. All right. Again, the order of these 3 cases, it's here, or it's left, or it's right, doesn't matter. But I need to cover all those cases. Right? Okay. Any questions so far? Turn node when we're done. That's it for recursive remove. I'm sorry, for recursive remove. But now we've got this helper function that we've invoked here. There's additional work to do. Once I've found the item that I want, we need to be able to actually remove that node. So one more helper method here. Private binary search tree node, type T, remove node. And I'm giving it just the node that I'm on. T, All right, so now I'm on to my 3 cases from the diagram, right? I've figured out where it is. I've identified where it goes. We need to figure out how to actually remove this thing. I'm going to need this data field to hold on to in case we do the swaparoo thing with the rightmost subchild of the left subtree. Right, we'll need that hanging around. So my 3 cases. If there's no children, if there's 1 child, left or right, and if there's 2 children, right? So we got to check, these all rotate around the children, right? So we got to ask a question about the children. So I'm going to ask about the left child first. If node.getLeft is equal to null. Well, what do I know if node.left getLeft is null? Then I'm in the case where there's not 2 children. There might be 1 child on the right, or there might be no children, right? We don't need to actually figure out which, because either way, what we're going to do is return what's on the right. I see how that covers 2 of my cases. If the right child was null, this returns null, which is correct if I have only a single node that I'm removing with no children. Or if it only has 1 child and that child was on the right, this is going to promote that child up, eliminating this node that's here in the tree. Right? Kind of tricksy, but if the left was not null, then I need to ask, well, what about the right side? If that one is null, well, then again, there must have only been 1 child, and it's the child on the left, if I've made it this far, right? Because left is not null, but right is null, and so I just need to return the node that's on the left. All right, that nicely handles my first 2 cases, right? Oh, the 3rd case. So what do we do if it's the 3rd case? Well, we need to be able to find that rightmost subchild of the left subtree. That in itself is an involved enough function that I'm going to once again defer to a helper function here. We'll punt and say get predecessor, which is a fancy way of saying get the rightmost subchild of the left subtree. Node.getLeft. We could write that code here in line, but it's just going to look messy. So let's assume that data is the data that we've grabbed from that predecessor. And so I can take the node that I'm on and replace the payload with that data. Right? This is the swaparoo. I found that predecessor node. I'm taking its payload, putting it in place here. The binary tree remains sorted. And then I can say node.setLeft, recursive remove the data from node.getLeft. I reinvoke my recursive remove function on the left subtree saying, now get rid of that node that has the data that I just stole from down lower in the tree. And this totally covers all of our cases. With me so far? Okay, so the last piece is this get predecessor function. This is surprisingly easy because all this needs to do is go as far to the right in the subtree as it can. Right? And then we've identified the item. All right, so that's like a 4-liner. It's in the book. It's super easy. Yeah? Katie? Yep.
That part, it'll remove if you find the left node. It's called rec remove, so it finds.
So I'm grabbing its data here. I've made a copy of its data. I'm replacing it in the node that I'm on. That's the red node from the diagram. And the blue node then needs to be eliminated from the subtree. And I've already just finished writing a function that will do that for me. It's the recursive remove function itself. Right, so we start the whole process again to get rid of whatever that node was. So the only bit we're missing here is the get predecessor function, which is super easy. We just head as far right as we can, stop when we can't go right any further, and we've found whatever the predecessor is. Which is exactly what Alex suggested, right? Okay, questions? Did you understand this? Be honest. Can you do this? Like if there's an exam question that asks you to describe in diagrammatic form how you remove something from a binary search tree, can you do that? I wouldn't expect you to be able to regurgitate all this code in an exam situation. It took us 4 lectures to get all this code up here. Granted, we talked about other stuff, right? But I would expect you to understand what the code is doing and to be able to functionally draw what it's doing and maybe to write small pieces of it. All right? Any other questions? All right, good job, team. That completes our binary search tree chapter. I'll probably say a little bit about tree variants next time, and then we're off into the maps chapter.